Here are the worked through synthesis examples from chapter 20, and I chose to write these out in advance and just talk about them in the interest of efficiency. So we have to take this alkyl halide and make this secondary amine. The only way we have of making a secondary amine at this point is by reduction of a secondary amide. There's no other way to do it. And we can make the amide in turn via two steps from the carboxylic acid, and we can get the carboxylic acid by carbonating the alkyl halide. So we're actually making two bonds here. So first we'll do the Grignard. So we make the Grignard, we carbonate it, we protonate it with acid because carboxylic acids are acids and they're not going to get completely protonated with just water. We make the acid chloride, and then we react the acid chloride with excess amine. That looks like a relatively inexpensive amine, so we can go ahead and sacrifice it and let one equivalent of the amine make the amide, and then the other equivalent of the amine neutralizes the hydrogen ion that's formed in this reaction. And then finally, we can take the amide and reduce it with an excess of lithium aluminum hydride, followed up with water, and there's our secondary amine. So in number 2, we start with benzene, and we need to make a bond to the ring, to the benzene ring, and in doing so add 2 carbons. And generally, if you're adding 2 carbons, a great way to add 2 carbons is by using an epoxide. So let's work backwards here. Again, if we if we have our group here with the 2 carbons and a bromine, then we can react this with the acetate ion to make the ester, and then working backwards we can make this alkyl bromide in a couple of steps from the Grignard. This is not the only way to do this, but it is a way to do it. So we'll add bromine, make bromobenzene, we make the Grignard, we add the epoxide to the Grignard, and remember that the epoxide is a synthon for 2 carbons, and that gives us this primary alcohol. And at this point, we have 2 options. We could actually take this alcohol and react it with acetyl chloride and make this ester. Just for the purposes of demonstration as much as anything, I chose to use this other way of making an ester so you could see it. So we can convert the alcohol into the alkyl halide with PBr3, and then do an SN2 reaction to make the ester, where we have this acetate ion as the nucleophile, and that will make the ester. There is nothing better about this pathway than there would have been necessarily by taking this alcohol and using a carboxylic acid or an anhydride or whatever, but I just wanted to demonstrate a different method. So you kind of need to look at 3 and 4 together, because in both cases you're starting with the same starting material. But in one case, your final product has the oxygenated atom is 1 carbon away from the ring, whereas in the other case, the oxygenated atom is on the ring. And that's going to impact how you make the bond. So we're still in both cases, we're still going to be making a carbon-carbon bond between carbon 1 next to the ring and carbon 2, but which piece we use to make that carbon-carbon double bond that's a nucleophile and which is the electrophilic carbonyl is going to be different. So here, since we want to make this bond, and we need the oxygen on the other side, this part is going to be a nucleophile, and this part's going to be the carbonyl. So in order to make this part into a nucleophile, we have to make a Grignard, Then we can add our carbonyl piece. So there's the carbonyl piece. And then we'll follow up with water to get that alcohol. And then you just need to oxidize this with pretty much anything to make the ketone. So remember, if you can make a secondary alcohol, you can make a ketone and vice versa. And here I kind of showed the working backwards process of that. So now in number 4, the contrast is we still have to make this bond between carbon 1 and carbon 2 relative to the ring, but now the left piece that's part of the ring is going to get turned into the carbonyl, and the other piece is going to come from a nucleophile. And that's just being set up by which carbon in each case is the oxygenated carbon. So working backwards, we need to figure out how to if we have this piece, which we can get from this piece, then the nucleophile can be our alkyl halide. So in other words, if we can convert the bromide into an alcohol, the alcohol into an aldehyde, and then finally add the Grignard to the aldehyde, we'll get the secondary alcohol. So first step, really easy, straightforward, nothing fancy here. You just add hydroxide, does an SN2. We need to oxidize this with PCC so it stops at the aldehyde. And then just add the Grignard piece and we're done. There's no final oxidation step here because our final product is an alcohol instead of a carbonyl. And for good measure, I showed the preparation of the Grignard. So make sure you look at these two and you understand how the carbon-carbon bond is made in each case and why it was chosen the way it was chosen in terms of which side is the electrophile and which side is the nucleophile of the new carbon-carbon bond. Because that's why I picked those two examples. All right, so now we have 5-membered ring with 1 carbon. So we're going to have to do something to make a bond between carbon 1 and carbon 2. And here we don't necessarily have the same restrictions we did on the last two because there's no functional group. There's no oxygen here, there's no oxygen here to drive which piece needs to be the carbonyl. However, I chose to have the left side piece be the carbonyl because we're starting with a carbonyl there. It makes sense. And then the other side will be the nucleophile, which will be the Grignard. So if we make this bond and the left side is the carbonyl, that's going to have to come from this alcohol, and this alcohol in turn comes from this aldehyde and a Grignard. So again, moving forward, what we need to do is reduce the carboxylic acid to an aldehyde. And there are a couple ways you could do it. You can convert it into an ester or into an acyl halide, and then use one of the special hindered reducing agents to go to an aldehyde. Or you could follow the advice of the UCI professor and reduce it to all the way to the primary alcohol with lithium aluminum hydride, followed by water, and then oxidize it back up with PCC to the aldehyde. I think it's the same number of steps either way. Now we can take this and react it with our Grignard, which will give us this alcohol. And now all we have to do is the thing that we normally don't want to do, which is to get rid of all the functional groups. I chose this particular pathway because I thought it might be a little bit cleaner. So I chose to turn this into a better leaving group using tosyl chloride. What I'm trying to avoid here is rearranging the carbon chain. My concern was if we tried to just dehydrate it, that what would happen is we get the double bond there, and then the water might add across the new double bond, and eventually you could end up with this, say, a carbocation here, and then you might get rearrangement. So let's just be safe and stick with things that aren't going to rearrange. The rearrangement may not matter because I don't think it's going to impact the carbon skeleton, but it's going to give you messy mixtures of products and make your workup harder. So I make the tosylate, and then either sodium ethoxide in heat or maybe even bring out the tert butoxide because we want to make sure we get elimination and not substitution. And then finally, we can reduce the double bond. Now, at your pay grade, if you had used concentrated sulfuric acid to do this, I would have been fine. I'm just trying to point out some of the pitfalls that occur with some of these. And finally, number 6. Now we're going to use some chemistry from chapter 18 because we have to make from benzene this di-substituted benzene. And there are 2 groups on it. There's a bromine, which is an orthopara director. Halogens in general are easy to put on, and they're not going to do much in terms of reactivity once they're on. And then we have this piece, which is a meta-director. So clearly we're going to have a carbonyl here before we add the bromine because we want this to go meta, not para. So we could just brominate this ester and the bromine will go there. We'll get this ester from benzoic acid, and we can get benzoic acid from, I think for the 3rd time in this set of problems, carbonating a Grignard. So bromine and iron makes bromobenzene. We carbonate the Grignard. We add acid. We make benzoic acid. And then here I chose to do, to make the ester sort of just the traditional way using the Fischer esterification. And then finally, don't forget the last step. Don't forget to finish off with the bromination. And, there are a couple ways you could have done this. You really could have brominated at any point from, I guess you could have brominated this, or you could have brominated this. I don't think it really matters